Some of the other probability rules that we're going to go over are listed in 6.9. We're going to go over what a compound event is first. You can probably guess if you know what an event is, or a simple event. A compound event is an event that is defined by combining two or more events. Alright, so if you have multiple events, then that would be a compound event. It's not a very hard concept to understand. Sometimes events may depend on each other. Sometimes events may be independent and not depend on each other. There's lots of different compound events. A lot of times the way that this is described is by using Venn diagrams. So say you have some event that happens here. Let's call that event A. And then you have another event that happens here, event B. Now, the way this is drawn, event A and event B do not have anything in common. However, if I had this as event A and this as event B, then I have a part here that overlaps. This part here, this is called the union of events A and B. So if you have a set of outcomes that are included in both A and B, then that's the union of events, and mathematically that can be written as this here. If you remember from college algebra when you're going over domain and range, a lot of times when we list the domain, we list interval notation, and in between each set of ordered pairs we'd have this symbol right here, and that means union with. Okay, so if you see A union B, then that means that we have a part of A and B that are the same. Okay? So this part right here where they are the same, that's called the intersection. Alright, the complement of an event. This is a very important concept. The complement of an event is the set of all outcomes in the sample space that do not go with whatever probability we're trying to figure out. So let's say that the probability of having exactly 2 girls from 3 births, we know that value, right? We figured that out. We said that was 3/8. Well, the complement of that would be the probability of not having exactly 2 girls from 3 births. You know, that's a lot of writing there. usually a complement is written by writing the probability, in this parentheses, you may just see probability of event A, or you may see probability of, like I have it here. But if you want to denote that it is a complement, usually a line is drawn above the actual event. For example, if I have the probability of A, its complement is an A with a line drawn over it. Or you may see your book here uses A, and then it has a, almost here in the exponent place, it has a C. Well, I've never seen this notation anywhere but this book. This other notation, if you see me write that, that means complement. And so the complement is going to be very important sometimes, because sometimes using the complement will help us figure out the actual probability a lot faster. Alright, so if we take the probability of A plus the probability of not A, or the complement, then that's going to be equal to 1. Because the probability of something happening plus the probability of something not happening has to be equal to 1. Alright, so we can actually treat these like variables. And we could say the probability of something not happening, or the probability of the complement of A, is equal to 1 minus the probability of A. And so the easiest example that I can give here is if we have the probability of having exactly 2 girls from 3 births, but we want to know the probability of not having exactly 2 girls from 3 births, then I can say that has to be equal to 1 minus 3/8, which is 5/8. Alright, so 1 minus the probability of an event happening is equal to the complement. Your book says that events, or I'm sorry, 2 sets are mutually exclusive. If they have no points in common. And so that would be maybe one event doesn't depend on another event. Like up here where I wrote down event A and event B, those 2 events, or this set of A and B, those are mutually exclusive. That's also called disjointedness. That's a fun word. Disjointedness. Show that to your English teacher. Alright, so if 2 events are disjoint, then you could list all the possible outcomes in two different sets, and they would not overlap. All right. Here's an example of using the complement. Consider the event A, annual income is greater than 50,000. Suppose the probability of A was 0.08. Determine the probability of observing someone whose income was less than or equal to 50,000. Okay, so the probability of A is greater than 50,000. The complement of greater than is less than or equal to. So the complement, you could denote that by, your book uses this little c here. I'll use that just because your book does, but so that has to be equal to 1 minus 0.08, 0.92. So it's a 92% chance for whatever study was done here that the income is less than or equal to 50,000. All right, your book goes through another example on the tosses of a coin. It says, consider an experiment to see how many tosses of a coin would be required to obtain the first head. The first head could be observed on the first toss or the second toss, but there's no upper limit on the number of tosses that could be required. Therefore, the sample space for this experiment is the set of positive integers. Not only is the sample space infinitely large, but there's another problem. The simple events are not equally likely. This is potentially ugly environment in which to compute a probability. It says the complement, but let's make matters slightly worse. Suppose we want to know the probability that it would require 2 or more tosses to get the first head. This means we must compute the probability of 2, the probability of 3, and so on up to infinity, and add them up some way. The problem is rather insidious if approached directly. It says the solution, the problem becomes rather trivial by determining the complement of the event and computing its probability. So it says the complement of obtaining the first head in 2 or more tosses is getting a first head, or getting a head on the first toss. The probability of getting a head on the first toss should be 0.5, assuming the coin is fair. Therefore, the probability of 2 or more tosses to obtain the first head is equal to 1 minus the probability of a head on the first toss. 1 minus 0.5 equals 0.5. If that's a little confusing to you, it's okay. It's not a big deal. I can help you with that if for some reason that seems a little confusing. This kind of makes a little more sense here. If you look at this, the probability of someone making greater than 50,000 plus the probability of someone making less than or equal to 50,000 has to be 1, right? Either you make more or you make less than or equal to. So if you want to know the probability of less than or equal to, and you know the probability of more, then you simply say 1 minus the probability of more than 50,000. If your two events are mutually exclusive, like event A and event B, well, B looks a little smaller, but let's just pretend that it's not. That's disjoint events or mutually exclusive events. The probability here is equal to the probability of A plus the probability of B. All right, let me show you an example of this. Suppose the probability of A equals 0.27 and the probability of B equals 0.19. If A and B are mutually exclusive, what is the probability of A union B? So the probability of A union B, of course this probability couldn't be greater than 1. But if we know that these two sets are disjoint, then we simply say the probability of A plus the probability of B. So that would be 0.27 plus 0.19, or 0.42. Another, let's see, there's another example given on your PowerPoint. You can look through that. These actual sets A and B would be events, so things that could happen. So, and no, it doesn't make a lot of sense if you don't actually put, you know, real world things in there, but we'll get there. All right, that was this probability of disjoint events or mutually exclusive events. That was a law of probability. The next law is the addition rule. The addition rule says that for any two events, the probability of A union B is equal to the probability of A plus the probability of B minus the probability of, what do you think this means? This symbol right here, that means the intersection. So if you know that the events are not mutually exclusive, so they have some type of intersection there. Sometimes they do, sometimes they don't, right? But if we know they have some type of intersection, you have to say the probability of A plus the probability of B minus that intersection of the two. Your book refers back to the problem that we worked out with salary. It says, suppose the marketing manager mentioned earlier believed that the probability that someone earns more than $50,000 is 0.2, and the probability that someone will subscribe to more than one sports magazine is 0.3. If the probability of finding someone in both categories, that means someone that earns more than $50,000 and someone that subscribes to more than one sports magazine, is 0.08, what is the probability of finding someone who is earning over $50,000 or subscribes to more than one sports magazine, or both? Okay, so we have these people here that earn more than $50,000, and we have these people here that subscribe to more than one sports magazine. If the probability of finding someone in both categories, right here, is 0.08, maybe I need to make my intersection a little bigger there, 0.08, then what is the probability of finding someone who is earning over $50,000 or subscribes to more than one sports magazine, or both? Alright, so the probability of A union B equals the probability of A minus the plus the probability of B minus the probability of the intersection of A and B. Alright, so the probability of A is 0.2 in this particular problem, plus the probability of B is 0.3, minus the intersection is 0.08. So if you add those two decimals together, you get the first two, you get 0.5 minus 0.08. That's going to be 0.42. So the probability of finding someone who's earning over $50,000 or subscribes to more than one sports magazine, or both, is 0.42, 42%.